Hey, here we go with a look at acids and bases. Yeah, I know. Yeah. Let's go ahead and look at this area. We'll spend more time on this in A&P2. This is an extremely critical area for nursing and for medical in general. But today I want you to have just a sense of what acids and bases are, kind of definitions of acids and bases, some examples, and then what about buffers? Why are they so important in keeping us alive? First, some definitions. What is an acid? Let me move me over here. What is an acid? What is a base? An acid, by definition, is some chemical or substance that when you put it in water is going to generate hydrogen ions. This is a hydrogen ion right here. It's a hydrogen with a positive charge. What it really means is it's a hydrogen as a proton with no electron. That's kind of technical. But HCl, if you put it in water, because of the nature of the bonds that hold HCl together, it's going to break apart and form hydrogen ions and Cl minus, chlorine ions. So HCl in water is going to form H and Cl. This is hydrochloric acid. When you put this substance in water, it generates or produces lots of these. Now, depending on how strong the acid is, tells us how many of those it produced. But here are some other examples. Acetic acid and carbonic acid, again, when put in water, are going to break apart and they're going to produce at least some, well, a number of these hydrogen ions, these protons, and therefore they are classified as acids. Bases are those things that are kind of on the opposite side. They take up hydrogen ions or protons when dissolved in water. So here is an example of one. This is sodium hydroxide, NaOH. If you put this in water, it breaks up into sodium ions and hydroxyl ions, OH. So hydroxyl ions, because they're OH negative, are going to find spare unattached hydrogen ions in water and form, again, H2O. So by definition, hydrogen ions, substances that take up hydrogen ions, are considered bases. Some examples in the body: ammonia. We produce small amounts of ammonia. And then bicarbonate ion, which is a critical one we associate with our blood. So again, by definition, an acid generates or produces hydrogen ions, and bases are those substances that can take them up. So when we talk about the pH and the pH scale, this literal, let me write it here, when we say pH, the little p in chemistry refers to concentration of. The pH scale really represents the concentration of hydrogen ions in solution. So there are substances, like if you have pure water, when pure water breaks apart, it does produce a hydrogen ion and it produces OH negative. Now, wait a minute, Mr. B. You said in the last video water stuck together. Most of the water molecules are going to be very tightly close together, but some of them are going to break up in solution. If you have the same number of hydrogen ions as hydroxyl ions, that's referred to as a pH of 7. Now, you see -7 there, and that might be a little confusing. What pH really is, and we won't go down this road too far, so don't panic, it is the log of the concentration of hydrogen ions. And when we say 10 to the -7, again, let's not get too detailed here. Rather than referring to negative exponents when we talk about pH, because this really means a concentration of, as this is the negative, it's the negative log of the concentration of hydrogen ions. Do not panic, you don't have to calculate that. What we're doing instead is saying, if it's -12, let's just call that, well, sorry, that's OH. If it's a -2, then we say we're going to call that pH of 2. If it's a -9, we're going to call that a pH of 9. So don't panic, but if you see a number like pH of 6.5, that really refers to a concentration. It's telling you how many hydrogen ions are in that solution based on that substance. So when we look at pH then, we can look at a scale where 7 is considered neutral because we have equal numbers of these. But if I go this direction, then this makes it an increasingly stronger acid. For example, 10 to the negative 6 is really close to 10 to the negative 7. 7 and 6, that's not a big change, so that's not considered a very strong acid. That's kind of a weaker acid. But by the time I'm up here, 10 to the negative 2, that's a much more concentrated, because again, negative exponents kind of work the opposite. So negative 2 is a far bigger concentration of hydrogen ions than 10 to the negative 6. Or, if this is a little bit confusing to you, when we go this direction, we get a stronger acid. If we go this direction, we get a stronger base. In other words, if I go this way, I produce more and more of OH negative ions that can take up more and more protons. So when we look at this chart then, this chart is showing us that pH is really a scale, that we go from 7 down to 0, extremely strong acids. We go from 7 to 14, extremely strong bases. But notice where most living things are in terms of our solutions. You see urine, you see saliva, you see blood, semen, even, they don't have it on here. Oh, there it is. Gastric juice at a pH of 2. So you see that even in our body, not the pH of all solutions isn't the same. There's slight differences in concentrations of how many of these we have in some places versus how many of these we have. So again, it is a scale, and the term you'll see also is alkaline. Alkaline refers to a weak base or a strong base. And again, just to remind you one more time, if I go this direction, I'm getting stronger and stronger bases. If I go this direction, I get stronger and stronger acids. So don't think that acids are worse than bases. It really involves what concentration of hydrogen ions do you have. And when we say your pH is 5, that's telling us a specific concentration. And you'll see in a second why it's so important that we care about that concentration. Here's just some pH normals, just to show you how the body is not the same all over. We'll focus on this one in particular. Blood, 7.35 to 7.45. That's a very narrow range for pH. Notice other ones are going to be more variable. Your duodenum or your feces may be far more variable based upon your diet. If you have a lot of acidic foods, then you're going to produce probably more acidic feces. If you're going to have more basic foods, then your urine actually pH may change quite a bit. But these norms tell us quite a bit. If your pH of your spinal fluid, for example, is 7.2 or 7.7, it tells us there is a severe disruption in your homeostasis because your pH, the chemistry of that particular substance, is incorrect, probably indicating disease. So what? Why does it matter? If the pH is a little bit off, so what? Big deal. Acidosis and alkalosis are huge medical issues and potentially fatal issues because they are disruptions of homeostasis. In acidosis, I have your body fluids, but we're talking in particular about blood. If your pH of your blood drops below 7.35, and again, 7.35 to 7.45 is considered the normal homeostatic range of blood. So if it drops below 7.35, then you're going to be diagnosed with acidosis. Your blood is becoming too acidic. And you're going to say, but wait a minute, pH of 7 is neutral. How can that be acidosis? Because it's becoming more acidic. Some causes advanced emphysema or asthma. And you're thinking, well, why would those cause acidosis? One of the things that happens when we don't breathe out very well is we keep CO2 in our bodies. CO2 actually combines with water to form acid. So the less efficiently you breathe, the more acidic your blood becomes. Somebody with advanced emphysema or advanced asthma is going to have a very difficult time breathing, and their blood becomes more acidic to the point it actually can push you into acidosis. This depresses the central nervous system, so it depresses your brain and spinal cord. Someone can become comatose, and if the pH continues to drop and we can't reverse it, it's fatal. Alkalosis is going the other direction. And you're going, again, 7.45, I mean, really? It's that tightly controlled? Yeah, because if you have conditions like hyperventilation, or you ingest a lot of sodium bicarbonate, or you happen to get rid of too much hydrogen ion, you begin to accumulate OH negative. And this is going to lead you to alkalosis. And this is going to hyperexcite your nervous system. It's going to cause spasms and convulsions, and once again, possible death. So you can see right there that, boy, we better be careful with our pH. We better not let it drift too low. We better not let it get too high. Fortunately, we have systems in place that that help regulate our pH. We have buffers, and I don't want to get you too confused or weirded out by this equation here. But there are proteins and other molecules and other systems in our body that can prevent large changes, large swings in pH. They can either release or absorb hydrogen ions and thus prevent our pH from changing too much. Here's just an example. This is going to be one that we associate with the blood. CO2 in water forms this bicarbonate. Bicarbonate ion, rather, here is going to see it's an OH, it's a negative, and we have the hydrogen ion, we have the proton. This can go back or forth depending upon the need. If we need to absorb hydrogen ions, the reaction runs this way. If we need to produce them, it runs that way. So this kind of is like a seesaw. We have these proteins that can actually capture or release hydrogen ions depending upon the need. We'll get far more into buffering systems in AMP2 because there are some extremely critical ones that can, if disrupted, can lead to respiratory acidosis or metabolic acidosis. For now, I want you to focus on what are acids, what are bases, relative strengths of acids and bases, and then ultimately why buffers are so important. That wraps up this video. One more coming. Thanks.